Good afternoon. I'm Bill Elm. Let me thank ASME and the session sponsors for being flexible, but I was unavoidably drawn away, and we're going to substitute with this video. We'll get to the end, and we have a substitute for taking some questions. We're going to focus today on cognitive systems lessons learned related to things that are absolutely relevant to key enablers for the SMR control room concept and what that really means for operator Tradecraft, so that we don't have to reinvent the wheel and we can take advantage of that. In order to sort of demonstrate and set the scene a little bit, we use this simple little game to really illustrate some of the key principles that map over into designing any decision support system in any control room. As we go through this, I'd appreciate it if we have a volunteer on this side that's going to play the game with me. But if I was there in person, I'd ask one of you in the audience to do it. So if you'd grab a piece of paper and sort of try to play along a little bit to get a sense of the demonstration here, then it would actually help us out. So I'll explain the rules to you. The overall goal is to be the first one to get to 3 pieces that sum up to 15. So a 9 and a 6 would not be a win because that's only 2 pieces. You can have extra pieces in your hand. You don't have to use them all, so you'd have spares that are not in your combination. But you want to get the first 1 to 3. We're going to draw one at a time by alternating. I'm going to let you go first, which is a strategic advantage. Once you take a piece, you own it. Once I take a piece, I own it. We'll alternate until we either run out of pieces or one of us gets to 15. The first one with 3 pieces that add up to 15 wins. So if you understand the rules, we'll get our demonstrator in here and we'll go ahead with the game. So please try to play along as we do this, and then we'll come back around and show you what the point is. On your piece of paper, you can draw something like this. These are your game pieces up here. There's an area here to write. Our demonstrator here will play along, and then we'll come back around and review the game. So whenever you're ready, go ahead and take your first piece.
I'm going to take 8.
She takes the 8. I'll take the 5.
I'll take 3.
3,000. She takes the 3. I'll take the 4.
2.
2,000. Okay, so she takes the 2. I'll take the 6, and I win with the 6, 5, 4. Okay, so you saw the game being played. You heard us go back and forth. I was playing from a representation here on the right, a decision-centered design, in a sense a design that has learned the lessons learned of cognitive systems engineering that we're going to be talking about. This was the system that we offered to our demonstrator. So just to recap the game, her first move was an 8. So she opened with an 8, took that piece. I went over here and did that. My move was a 5. On this spatial representation over here, that 5 is key terrain. It's involved in 4 possible winning combinations, and I'm not doing any math over here. I'm just looking for spatial arrangement. So the 5 was off the board. She came back and took a 3. I went over here and gave it to her, and immediately spatially saw that I needed to block that offensive thrust, which also puts an offensive thrust toward me. And at that point, you saw one of the difficult things here. You saw her shake her head because her plan was an 8-5-4, and I had just disrupted that plan. So we've just made the operator do a reactive replan in the middle of an operation. That's a difficult thing to do in real time under time pressure. So just that little bit of time pressure makes a big difference. So I came back and took the 4. The 4 is off the board, and you're getting a sense that I'm able to respond faster. Again, the key move would have been to shift to defense here and block me, but it's very challenging to see that I'm on an offensive thrust that she needs to shift to defense. We call that the competing goal dilemma. When a piece has both an offensive potential and a defensive potential, you have to remember to check both goals, and that's very difficult for humans to do in their short-term working memory. So plan disruptions like that are very challenging. She came back and took the 2, which you can see is already a disrupted path. I've already blocked that, so there's no threat. That leaves me open to take the 6, and I win with a 6-5-4. So it's actually effortless for me to come in here and grab the win because, again, I'm playing a spatial adjacency decision aid where this idea of winning triples is compiled into the space. The data is really just identifiers of the space for me. Here, it's all about the data. I've got an 8, I got a 3, I need a 4 to win. The 4 is blocked. How do I shift? Do I try to react? There's a lot of math going on toward 15 on this side of the board. I'm not doing any math when you have the right affordance, the right decision-centered design. So hopefully you have a sense of both the speed, the ease, the intuitive nature of doing it when the affordance, in Don Norman's sense, when the affordance is really matched intuitively to the work that's going on. The challenge now is how do we do that in a nuclear control room, in an SMR control room setting, which is even more difficult. The principles behind all this are called cognitive systems engineering, and the thing to realize is basically every bit of technology that we field is really building a joint cognitive system with our user. Classic systems engineering sort of puts a divide over here, where the system that we build is built notionally to do some work in the world, control the plant, monitor, command and control, whatever it is. And there's a training chasm here and an operator's manual, and the user, that adaptive agent that we put up here that's going to make us successful with our system, is on the other side of a systems engineering divide. So what cognitive systems engineering is really all about is here in the center, recognizing that the systems we build have to be built with knowledge of how people think to get work done in the world, and you build a fundamentally different system in the middle. You build that system like here on the right, where you recognize these decision-making requirements. So it's really this combination of mission, user, and the technology to build this closed loop. So if you're sort of a control system-minded person, it's like closing the loop in the control system, and we call that a joint cognitive system. The SMR control room is a joint cognitive system. Now it's multi-person, so we have multiple users. There's multiple system, subsystem components and instances of each system, and in the SMR case, multiple reactors to control toward one overall safety mission. All of that has to be coordinated as a joint cognitive system. So there are lessons learned both in process control, nuclear power plant control room design, and in many other domains that really should be brought in here and thought about as the SMR control room gets finalized. If you want to read about it, here's a couple of books we'd recommend by Woods and Holnagel. One is kind of the background, one are the patterns. Patterns are really the case studies with these lessons learned embedded. If you want to read more about it, you can check our website or you can look in these books. There's lots of other books. I'd recommend those too. The other point here is that what we're talking about, cognitive systems engineering, that joint cognitive system, really applies whether you're building a widget or an app for a cell phone, a single display, a dashboard, whatever you want to call it, a relatively complex individual workstation with multiple displays, all the way up to a multi-person, multi-system operations center. Those issues of mission, user, and system that we build apply at all those scales. It's a little simpler when the scale of the problem is small, but it's even more critical when the scale of the problem is large, like the SMR control room will be. Some of the basic ilities underneath cognitive systems engineering. So if you're looking for sort of gut check indicators about whether the design is operating right, it has to be able to achieve these 5 key factors. Observability in terms of that taking the lid off that black box, revealing the underlying function in an intuitive way. This is what doesn't happen if you have data overload. The data doesn't really provide good observability, good intuitive understanding of the situation. You don't achieve situational awareness unless you reveal the underlying underpinning of what's going on. We can talk a little bit more about that. Commonly, systems that do this well reveal what we call the lift, thrust, and drag of the work domain. So that's kind of a reference to flight. Ultimately, a pilot is managing lift, thrust, and drag of that aircraft, regardless of whether it's a propeller-driven airplane or a rocket-driven airplane, to generate that thrust. It's a glider. It has no thrust. These are really the underlying physics, the functions, the abstractions that characterize expert performance. Observability reinforces that. As soon as you build in observability, the operator wants to direct it, wants to be able to drive that, steer that, and have some control on those things. You'll see some discussion as we go forward, lessons learned about observability and directability in nuclear plant control. As we continue to add automation into the plant, and this is an area that is classically underbuilt, observability is classically underbuilt, teaming with automation is classically underbuilt. The assumption is that the automation runs fine, the user will take control if they need to. You have to build that automation to have observability of the automation itself, so that you can actually get a cooperative teaming effect with your operator Again, that's classically an area that is under-designed and under-supported. Support for directed attention, that's really what's going on behind what you would call an alarm system. This is really effortlessly helping the user know where to look. Klaxons that make your ears bleed are not very effective in terms of helping me know where to look in an elegant, intuitive, effortless kind of way without a high-cost interrupt. If our alarm system, our directed attention support system, is too heavy-handed, it interrupts before I need to be interrupted. I'll never get any work done. Resilience really relates to robustness. This is error detection and recovery, again, a kind of a control system, serious thing. Overcoming the brittleness of the automation when the automation is out of its zone, being aware of that, and also being able to deal with novel situations that have never been seen before. So the robustness in your control room ultimately comes down to your user being the adaptive problem-solving agent in that closed-loop system, and novel situations become the job of the operator, not the job of the technology. And that's essentially why you keep an operator in the loop, in the procedures, and in the room. The goal of SMR to do the same thing that the UAV community wants to do, to have multi-asset few controllers, so there's a high N-to-1 artifact or system to controller ratio. Everybody wants to do that for all the same reasons. The challenge now is how do you build an effective joint cognitive system from your control room. So as I'm going to move through maybe some case studies here, and we'll see if I can make some of these points. This is kind of a SNUPS era plant right here, sort of the 1970s. Obviously, it's an analog board, got a little bit of digital plant computer stuff in it. The alarm system, the directed attention support system, has a spatial distribution here. In general, the board is aligned to sort of correspond these data-centric single alarm point triggers to the appropriate systems as that system boundary moves around the room. So there is a spatial distribution, there is some dedicated space. So that tile is always well known. This tile is always well known. Humans are very good at learning where things live in that space. As we studied after 3 Mile Island, we studied the alarm avalanche that in fact did not support the users in helping to detect and recover the plant. We came up with these principles about alarm systems, characteristics of alarm systems to make them good ones. It has to be sensitive enough that during that initial departure from normal, it's giving you some early mitigation opportunities when you still have room to recover, when you still have room to mitigate that disturbance as early in the event evolution as you can. Yet it has to be robust to large disturbances, meaning it can't avalanche things when big things go wrong or late in the evolution of the event. The analog control panel had relatively high sensitivity, but it was not robust when things got large. The alarm rate actually added to the data overload. There's quotes from TMI operators that say things like, the alarm system didn't help me, and in fact, I wish I could have taken it out of the control room during the event. So that's actually a pretty good indicator that we did not achieve robustness with this directed attention support solution. And again, an important thing we talked about, has to be resilient to these novel, unforeseen situations. Every one of these alarm triggers is predefined, pre-analyzed. How do you achieve that robust behavior when something breaks nobody thought could break? Again, TMI had some of that characteristic to it. That exact situation was not really pre-thought very well. Again, you have to support that adaptability, that adaptable performance of your user. The real elegant question here is how do you provide just enough information for the operator to decide that they want to stop what they're doing and move to a new focus point, a new issue, without consuming that attention. If you're familiar with your peripheral vision, does this for you all the time. You see something moving in your peripheral vision, you'll orient your foveal vision and look at that. It's also called the cocktail party effect. If you're in a busy, crowded cocktail party and somebody mentions your name across the room, you'll get an audio tip and you'll actually be able to look at the person that said your name. But if I asked you, were you listening to that conversation, you would say no. So there's this elegant pre-attentive set of focusing mechanisms that humans have. So again, if we can factor that into how we design our support systems, we can get that non-interrupt, that low effort attention direction support. So to achieve some of these criteria down here, we worked on a system in the 80s in direct response to that. This is the system, so this is in the 80s over here. And you'll see that we preserve that spatial distribution. So there are dedicated regions of the board. This is one board section. It runs around the rest of the room. And we've got these key plant functions. We've got lift, thrust, and drag dedicated into that space. And we've also got goal versus process disruptions. So we've got energy balance kinds of things going on inside our temperature space. So without even reading the alarm panel, we get the same kind of recognition that we had here, yet we have some variable message capability within each one of those areas. So we were able to have a low attention demand and be highly informative. What function, what piece of that function is being disturbed? Has it propagated up to being a significant goal disturbance within that function? So we had some robustness. We had very good sensitivity. It was a dark board till the initial thing happened. We could deal locally with local prioritization, and it was very resilient to novel situations because of its functional nature of that space being spread around the room. So that lift, thrust, and drag nature is based on a model of expertise, and that worked very well. This design is installed in one plant in the world. It changed their normal operation procedures, changed their emergency operating procedures, and was actually very, very good at some very, very insidious kinds of faults that were basically not well supported by a traditional annunciator tile system. So if we now consider that, so this was the 70s, that's a design I showed you from the 80s. This is actually AP1000. This design here was used going into AP600. And some things started being cut off as the technology evolved. I found this, so basically I guess my career started over here. And I was told last week that I've been in this business for a third of a century, so that's kind of over here somewhere. So this is me, kind of bracketing from here to there. And what happens is every time the technology changes, designers go back to the drawing board, and sometimes things get lost. If you look at the AP1000, basically the whole AP series control rooms, they don't have the same functional nature in the alarm panel, and they really don't have the same spatial distribution of alarming. The alarm system is now driven as a digital technology. It's fundamentally a list-based approach, which is proven as a lesson learned. So here I'm going to draw you a scrolled list-based sort of Google list return, except now you have last in, first out, rolling stack, chronological order. And this kind of keyholing, even if you put priorities on it, even if you put a cut line in the screen and probably one at the top, probably two at the bottom, you apply all these coping mechanisms, you do not get the same effectiveness in terms of that landmarking that occurs, that visual familiarity with location on the board, because a scrolling list is just a scrolling list. So we've lost some things in terms of spatial landmarking, this sort of local prioritization within these, we call them slots, within a function. All of that is now falling away as the INC goes from pure analog to digitized and now to a pure digital system where basically the digital INC is built with sort of a plug and play mentality. You lose some of your directed attention support. Now, as we move into the SMR control room, one of the key issues is the operating premise that the SMR control room can basically have 3 front row operators spread across the 12 plants. So here we have the 12 individual plant workstations. We have a common one in the middle, an overview center there in the middle. So there's your 12 around the side. The real challenge here that's implicit in this design is, can you achieve effective directed attention support so that this operator on this side of the room knows which of the 4 plants needs their attention at that time? It gets trickier if 2 of these plants need attention, and one of these operators has to now swing over, and one of the back row folks has to now basically reassign people to try to cover that. It's not enough to talk about one disruption where there's only one thing wrong in my control room, and it will be reported this way, it will appear on the board this way, my operator will detect it and respond to it. The challenge comes as multiple things cascade. An operator spills coffee on themselves, somebody is out of the room on a break, somebody else is now maybe new to the shift, and multiple things go wrong that have never been seen before and take some significant thought. So moving back and forth around the room, being able to shift attention between multiple plants is a critical support requirement from the joint cognitive system called an SMR control room. The UAV people, the UAV community across all the different platforms, Predator, Global Hawk, any of those, even the F-18 unmanned, they want to move to this kind of a problem. They want to have N plants to one operator. They, in fact, are currently still one plant requiring N operators, where N's on the order of 3 to control one UAV platform. Even with sophisticated avionics and automation, they are still about N equal 3 in terms of this operator to plant ratio. Here we're at 4 to 1, 4 plants to 1 operator. We've got to get directed attention support right. And frankly, there's a lot of things that have been lost and thrown off the boat as we move into this kind of an architecture. I zoomed here so that this operator this supervisory station here at the beginning, or at the center of the room, has this monitoring panel at the top. And these are configurable displays. I overlaid this here, which was from some early SPDS work at Westinghouse from Dave Woods, in terms of these key functions and this normalized polygon being a very elegant, intuitive, it's called an emergent pattern-based display, to be able to detect an off-normal system. And the characteristics of those off-normal systems are in fact learnable indicators, so the operator will be able to detect the shape differences and in fact have a sense of what is going on at the plant. So it's actually a good emergent alarm, if you will, for overall plant health, but it's very information sparse about what's exactly going on in that plant. And frankly, then even this row and column array here is going to be very difficult for somebody to take this. Again, if I put the egg crate back in here, this panel is which one? Is it this one? Is it this one? Or maybe this is 1, 2, 3, 4, and they go 1, 2, 3, 4. Even associating the spatial layout of that panel, which is obviously very compact and pixel friendly, in terms of its intuitive mapping to where I am in the room, is just that little bit of difficulty that you saw back in the game of 15 that can cause dilemmas and cause issues under stress, under novel conditions, in that place where you really want good performance from your operator. Just even talking about directed attention support, there are some things that could be improved and should be, in fact, focused on in order to get really good joint cognitive system performance from the control room technology and these adaptive agents that are part of that integrated control loop to really ensure safety in the plant. So again, combining the user with what we build in terms of the decision support environment, you get grossly different performance, just like we did in the game of 15. The other thing that's happened as INC has gone digital, the displays, that plug and play approach has really gone back to a lot of physical mimic, sort of P&ID driven displays. And there's been a decrease in the real plant functional kinds of representations, and that those functional lift, thrust, and drag type of representations are proven as critical for proper observability to achieve expert level performance. The research shows that experts think in abstract functions. If the board is giving you a lot of physical valve positions or physical flow rates and temperatures, the operator now has to be able to do that data to function mapping in the user's brain, and that is basically not something that humans are good at. Increasing the abstractions in the displays themselves and adding some better directed attention support based on lessons learned from the 80s will be critical to making the SMR a successful control room for the plant, for the overall operating concept. And again, I apologize for not being able to be there. I was called very far away, and I apologize we can't do live questions. But if you have questions and you want to email them to us, we'll try to give you a concise response and address those. I realize I went through this very quickly, and there's a lot of very deep research behind where these lessons come from and where these ideas come from in a cognitive systems engineering research standpoint, but applying that back to the design of our decision support environment. The real message here, you really have to design your systems by respecting, in fact, the way these other cognitive agents in your control room, your control loop behave, and you really have to design this joint cognitive system that really brings all three of these elements together. Again, I want to thank the session chair for allowing me to do this and apologize I wasn't there. Please send your questions along. We'll do the best we can.